pleasure today to introduce Jonathan Asaadi, currently at Syracuse University. Jonathan actually started in the University of Iowa, and I'm very pleased to say that Jonathan was one of the very first who started on a route that we now utilize very heavily, and that Jonathan was actually an REU student here at A&M many, many years ago. And because of that, he came to see what it is that we do. And we're so excited about what we do that he came here for graduate work. And we're very pleased to have him. Jonathan then came and actually worked with me on CDF on one of probably one of the most difficult analyses that I think that be. We had in our data what looked like a 5 sigma excess in the delayed photon, which we are very excited about. The problem was that we were using tools that were very different than everybody else. So this was really our baby. And the problem is when you have an excess in your data, you got to do everything before you can get it out. And only the very brave of heart are willing to stay in graduate school and to suffer through the 10 bazillion different things that could be what's going on and causing you to think that you have an excess when you don't. It was an exciting chase, and unfortunately, Jonathan did such a good job of finding all the little problems that nobody else ever had to worry about that he made it go away. So, Jonathan had a very exciting career at CDF, and we kept him a little bit longer, but because he was so well trained, he really hit the ground running when he went to the University of Syracuse. Basically, I didn't even have to write letters for him. He got a job offer before I even wrote letters. I think Jonathan has shown another set of bravery by leaving the comfort zone of the collider world to go to smaller experiments where he could have his bring his real expertise, his people skills, his nose for good physics to do exciting things where he could have a real impact in the neutrino world. And we're very excited to have him back after a couple of years so he can tell us about all the fun and exciting things he's been doing on the experiments like MicroBooNE and ArgoNeuT and those fun things. So I expect fun things from Jonathan, and especially for those of you who are students or young in the field, Jonathan was a leader in the snowmass process for the young physicists. So please get a chance to chat with him if you can. But in the meantime, please join me in welcoming Jonathan Asaadi.
Thank you, James, very much for that very nice introduction. So I'm going to get to tell you today about MicroBooNE and ArgoNeuT and the future of liquid argon. And so I have to start off with my don't let my cover slide fool you. Fermilab in Chicago don't look anything like this right now. They look more like this, and this is a picture from flying out during the polar vortex, which unfortunately I seem to have brought with me. And this picture actually reminded me of another picture I saw a long time ago. You remember this movie, The Day After Tomorrow, which is more what Chicago looks like right now. So thank you very, very much for letting me escape the snow apocalypse that's up there and come to what was warm and it will be warm again, I guess, Texas, to talk to you about these things. So I want to give you kind of a brief outline because I'm going to cover a lot of ground, so I want to lay the groundwork for it. I want to give you just kind of a broad overview of the physics now that I've spent a lot of time talking about in terms of the neutrino physics, and specifically a detector technology that I've gotten to work a lot on called the liquid argon time projection chamber. And then 2 experiments that have been utilizing this particular technology, ArgoNeuT, which is the Argon neutrino test stand experiment, and I'll tell you about some analyses that are going on in there. MicroBooNE, which is the micro booster neutrino beam, not to be confused with MiniBooNE because we name everything with a boon and we're terrible at acronyms. And then some of the future experiments where the liquid argon field is going in specific. So, of course, you start every particle physics talk with a picture of the standard model because it's written into your contract that you have to do so. And really at the coming out of the snowmass process and in 2012, there were 3 questions that were kind of really put forward by the community. Specifically, out of the discoveries given in 2012, what is the nature of this particle that looks like the Higgs boson? What is the majority of the matter in the universe, meaning that there's all this dark matter that we don't have to explain? And then the question I've been really focused on is what is the nature of the neutrino as one of these really fundamental and driving questions. So as recent as 1998, there was a very simplistic view of what the way neutrinos were. The neutrinos had 3 flavors. They interacted via the weak force, and they were thought to be massless. However, what we observed is that that's not actually true, and that the neutrino flavors mix. And so if you've ever seen these pictures, they have these standard model plushies to represent these particles. And what the mixing means is that they can change in their flavors when they propagate over some distance, and this implies that the neutrinos have mass. And this was really a new picture of physics that happened very recently in particle physics. So the way that these masses mix are parametrized through this really seemingly simple mixing matrix, essentially where you can take all the different flavor eigenstates and mix them with the mass eigenstates, and you can describe how this mixing happens between flavor and mass through a pretty simple unitary matrix, which I've shown here, and I've left off one term that has to do with whether or not they're their own antiparticle. But essentially, you can describe how these mass eigenstates change into the flavor eigenstates through essentially 3 angles in one phase. And, oh, am I still clicking? No. So, up to this time, we've measured 3 of these angles, and we're still left with the phase. Sorry, my slides are out of order. Anyways, we'll stay here. And there are still a lot of unanswered questions when it comes down to this picture, this 3-flavor picture that we have. Namely, what is the ordering of the mass hierarchy? Are there more than one or more of these extra flavors? And do they violate CP? And so in a lot of these ways, I'll come back to these physics questions. I just let you know that they're out there. But we have this very simple picture of how oscillation physics actually goes. But what this means to me as an experimentalist is actually much simpler. What it means is that when I have a neutrino source and I have those neutrinos that travel over a very small distance, they will maintain more or less their same flavor. Meaning if I have an electron neutrino, as it interacts in the detector, I'll see an electron. A muon neutrino, when it interacts in my detector, I'll get a muon. But if I allow my neutrinos to oscillate over a longer distance, travel over a longer distance, there's a probability that they will change their flavor. So if I start with a source of neutrinos that's all electron neutrino, every once in a while in my detector, I'll see a muon, meaning that that electron neutrino oscillated into a muon neutrino. And vice versa for the muon neutrino into the electron neutrino. So essentially what this means is that the name of the game is looking at the charged particles that are produced in the detector to infer something about the nature of the neutrino that was incident on it. So this gives you some very basics on what you need for a neutrino detector. Basically what you want in order to see the neutrinos that are interacting via the weak force, a really good strategy is make your detector as big as possible, which means you just put as many nuclei in the path of the neutrinos as you can. You want to pack as many nuclei as you can into the volume that you have. So you want to make sure that your detector is very dense, and you want your detector to be sensitive to neutrino interactions, specifically the charged particles that are produced when you have one of these interactions and the light that's produced along with it. And so we use the charge that's collected in the light to do some particle identification to determine what types of particles were created, and that tells us something about the neutrino. So at risk of showing a slide where there are likely more experts in the room than me, one very good example that a lot of people might be familiar with is the Minos experiment at Fermilab. It's an example of something that is very dense. Minos is made of steel scintillator paddles, and you don't get much more dense than steel. It's relatively big. It's 5,400 tons of steel in the FAR detector. And so they had this near-FAR configuration where we shoot a beam of neutrinos from Fermilab all the way to the Sudan and Minnesota. And so you get this ability to detect the neutrinos over the long baseline. And it's relatively sensitive in the sense that you can put steel scintillator, steel panels and then scintillator, and you can actually see what the interactions look like. So if you have a neutrino interaction that produces a muon, you get these paths that you can then trace back and say, aha, I've got a muon there. If you have an electron interaction, you see this large spread in dispersion and energy that allows you to start to identify if you have an electron interaction. So some other examples of neutrino detectors, I point to IceCube, which is a detector in the South Pole. This is 1 cubic kilometer of ice that they utilize. And it's not the most dense stuff in the world. You can imagine there are denser things than ice for a neutrino to interact with. It certainly is big. They don't make much bigger than 1 kilometer cubed of ice. And in terms of sensitivity, it's fairly sensitive, and it's really sensitive to high energy things. The way that they utilize this detector is they put these optical modules they call DOMs into the ice, and they string them down on 2-mile-long strings, and they look for the light that's created, the Cherenkov light that's created when a charged particle goes through. And so here's an example of a muon neutrino candidate and an electron neutrino, so you can see that you were able to do some type of particle identification. Another type of detector is these large water Cherenkov detectors, the example being the Super Kamiokande experiment. Again, water not being the most dense thing we have, this one is absolutely very big, and it's relatively cheap to scale this up. Water isn't terribly expensive when it comes to building this. And it's a very well-known detector technology. Here you can see an example of just an absolutely huge photomultiplier tube that gets installed everywhere inside this Kamiokande experiment. And so you can see what a muon neutrino interaction looks like. You get a nice crisp Cherenkov ring versus an electron neutrino candidate where it's a much fuzzier ring. So again, it's a fairly sensitive detector to the sort of things that we want. Now, you don't have to go too far back in history. In 1968 was the first proposal to utilize another material for a detector. In this case, the liquid argon particle detector. This was first put forward by L. Alvarez. I forget what L stands for now. But what was it? Louis Alvarez? Could be. But then in 1974, you had the first one of the first applications put forward by Bill Willis to use liquid argon as a calorimeter. And of course, again, to put something else that everybody in this room is more of an expert than probably I am, there are two very good examples of liquid argon being used in a calorimeter, specifically the D0 calorimeter that was at the Tevatron, and now the Atlas liquid argon calorimeter. So there's a long history of utilizing this particular thing as a detector source. And then in 1977, there was the first proposal put forward by Carlo Rubbia to actually utilize these really beneficial properties for a neutrino detector in specific. And so in this paper, which is incredibly short, he lists off all of these really good reasons that you would use liquid argon as a detector. So I just want to walk through them, and you don't have to squint at the screen. So the liquid nobles in general are very good particle detectors, and the reason we utilize argon as opposed to any of the other liquid nobles is, it has all of these properties that we really want. So specifically, argon is really abundant. It makes up about 1% of the atmosphere at 9,300 parts per million. That means it's really inexpensive to get because you can just distill it out of the atmosphere. And it can be cooled using liquid nitrogen, and its boiling point is around 87 degrees Kelvin. That means it's really cheap to cool and keep in the liquid phase as well, which is a really big benefit. Just in terms of cost, roughly speaking, you can get argon for about $2 per liter, as opposed to some of the other liquid nobles you can see get really expensive as you have to utilize them in larger and larger detectors. Argon is fairly dense. It's almost 1.5 times more dense than water, which means you're putting a lot more nuclei in the way of your neutrino beam. Argon ionizes very easily, giving you about 55,000 electrons per centimeter. It's not the most ionizing liquid noble, but it does a pretty good job and does a lot better than water. And as an added bonus, it produces a lot of scintillation light along with the ions that you're producing. And just as a kind of a neat side effect, it is transparent to the scintillation light that you produce, which means you can observe the scintillation light over really, really long distances. So in 2004, this is something that's relevant to people here at A&M, was the first use of a liquid argon scintillation light as a tool for dark matter through the WARP collaboration. This was done over in Gran Sasso. And this has given birth to a large number of other dark matter liquid argon-like experiments trying to utilize all of these really good properties. But of course, I'm here to tell you about neutrino detectors. I just want to let you know that this is a broad-based technology. So to understand better how the liquid argon is utilized to understand the neutrino-argon interactions, I want to just kind of walk through the general process of how it goes. So we fire our beam of neutrinos into the volume of liquid argon, and I'll say more about how we keep the argon cool and all the neat stuff that we do for cryogenics. And then once you fire your beam in, you will get an interaction every once in a while. That interaction will produce some charged particles that ionize the argon, as well as producing a bunch of scintillation light. And I want to take a moment just to kind of explain an aside on some of the scintillation light, because it's really interesting how this process goes. So there are basically two processes by which you get scintillation light in liquid argon. One is this self-trapped exon luminescence. The other is this recombination luminescence. And essentially, in the self-trapped exon luminescence, you get some charged particle that then charges your argon. The argon joins into a pair. Once that pair decays into its ground state, you get a photon out. Similarly, in this recombination, what you will end up having is you'll slowly separate the electron off from the argon. That argon atom then recombines to pair together. This electron orbits and then it again decays and gives you the scintillation light. The reason that this is interesting is that both of these processes form what you know as an excimer state, a Rydberg excimer state. And what's really interesting about this particular state is if you look at its energy level when it decays is 128 nanometer photon comes out. But then if you look at the first excited state of the liquid argon, that's well above that. That's what lets argon be transparent to these photons. So anytime you get this process that's going to give you your scintillation light, that light is going to be transparent in the argon, which means you can observe the light from very, very large distances. The other interesting side note that we'll talk about a little bit later is that as you increase your electric field to get that charge to drift over, you tend to kill one of these paths because you're moving that electron away, you don't get the recombination effect. So you get an effect of light quenching as you go through, so you have to make up for it in other ways. So now we've got these ultraviolet 128 nanometer phototubes. We put them over on one side of our detector, but the PMTs, the photodetectors, see visible light. They don't see ultraviolet light. So you've got to go one more step, and you have to have that light be incident on some wavelength shifting material. We use tetraphenyl butadiene, TPB is what we call it. And what it does is as the UV light is incident on it, it then re-emits light in the visible spectrum, and so your PMTs can trigger on that. And for the purposes of a neutrino detector, we use this light pulse to give us a T0 for when the event actually occurred in the detector. And there are a lot more details in all of the testing and everything that we do of our PMT systems. You can find the references down below. So this is a picture of the photomultiplier tubes, the PMTs that we actually utilize in one of the experiments, MicroBooNE, and you'll notice that there's this rather opaque white stuff over it. That's the TPB, that's the UV wavelength shifting material that we mount in front of the PMTs. So I've told you a little bit about the scintillation light. Now I want to tell you about the charge that we're actually going to utilize to determine what is going on in the event. So in order to get that ionization charge over to where we can read it out, we have to apply a very uniform electric field across the volume. And then we collect this charge on a series of sense wires that we arrange on one side. And we don't just use one set of sense wires. I just want to go crazy in PowerPoint drawing all of those wires. And so what you read off of the wires is the amount of charge that was produced in the event. And you figure out, because now you know when T0 is from your light pulse, you then say, how long did it take for the charge to drift over? And that tells me in 3D space where that interaction was. So I project that back into the volume, and that's where we get the name, a liquid argon time projection chamber. We're projecting how long it took for that charge to get over in order, based on the light pulse and the charge that we read out from the wires. So there's a lot of interesting physics that goes into just drifting the charge. I've made it sound awfully simple. Apply an electric field, let charge go. And there's a lot of different things that you can impact this measurement that you have to take into account. For example, how does the drift velocity depend? How do your ions diffuse through your liquid argon volume? And what happens to the ions as they drift over? So I just want to take a second to tell you about all of the physics that you have to study in order to really do this. The ion drift velocity turns out to be more or less an empirically modeled function that depends mainly on the temperature of your argon and the electric field you're applying. And so you can see here different bands for different temperatures of the argon as a function of electric field, what your nominal drift velocity is. This is from an Icarus paper, and similar measurements are done in the current neutrino detectors going on at Fermilab. And so it's this complicated looking function that you have to make sure that you understand to take into account to project back into the volume correctly. As well as once your ions are drifting, they also tend to diffuse, meaning that they spread in RMS. And the amount that they will spread is related to both how far they have to go, that's the z direction, and how much electric field you're applying, how quickly you're getting them over there. as well as what is the mobility, the electron mobility currently in the liquid argon. So your ions diffuse in both in terms of a transverse and longitudinal. And so the red line here shows you the measurement of the transverse component over various electric fields. And the blue line here shows you what you expect for the longitudinal spread in the charge. And just as a side point, you'll notice that there is one data point that harkens way back from a long, long time ago. I think the paper fell off the screen, of measuring the longitudinal spread. So this is something that's still kind of an area of active research to understand what causes you to lose some of this charge as a function of electric field. And then I put here as a side note, we don't actually count the number of charge. What we measure is the energy, and then we just use a real simple relationship to go back to the transverse and longitudinal spread in the charge. There's also a number of competing effects that happen to your charge in terms of charge recombination. So as your charge is drifting over, if it encounters any impurities, it will cause you to lose some of that charge. And the way that this happens depends on both the different types of impurities as well as their concentrations and the value of their electric field. So this is actually a really complex thing where you can see that the way that N2O affects your recombination versus O2 versus CO2 varies drastically. So you really have to have a good handle on what your impurities are in your argon to really make sure you understand the charge that's collected and be able to correctly infer back what you have going on. So this is why we take a great deal of time in all of these experiments to make sure that we measure and purify the argon in various ways. Okay, so now I've kind of given you a flavor or a taste of that we have our ionization charge produced from our incoming neutrino interaction. We've figured out how to get it to move over to some sense wires. Now I want to tell you a little bit about the physics that goes on at the wires. I've had to spend a lot of time kind of learning about this, and it's neat, it's interesting physics to me. So here you have an example of the wire planes that are in MicroBooNE. You have 3 wire planes, Y, V, and U, and they're separated by about a 3 millimeter gap in between them. Now what you really want is you want your charge to drift past the first plane, past the second plane, and collect on the third plane. That's the way you collect the most amount of charge and you get the most amount of information. So in order to do that, you have to know your electric field to a high degree of precision right as it encounters the first plane of wires. And then you have to apply a transparency condition. It's kind of a simple E&M problem. But the idea is you want the charge to pass by the first plane of wires. So your first plane of wires is negatively biased. Your second plane of wires is at ground. And your third plane of wires is positively biased to collect all of that charge. And so what you read out of your wires is a bipolar induction pulse on the first 2 planes of wires, and then a unipolar collection pulse that represents the amount of charge that you actually collected. So these 3 things combined allow you to tell you different information about the charge that you're seeing back in your volume. And so once you're all said and done, basically what you have is this. You have a bunch of charge that's created, it drifts over to the wires, and as it's collected on the wires, you'll see for the blue plane here, which is the induction plane, a bipolar pulse. And then you see down here a unipolar plane. And now you have a projection, 2 different projections at 2 different angles of what was happening in your volume, so you can project back and get a 3D image of your neutrino interaction in a great deal of detail. So this is an example event that was actually, this is real data that was collected by the ArgoNeuT experiment. And this is an example of the type of resolution we're able to achieve in these neutrino interactions. So what you have here is you have a neutrino comes in from screen left, it interacts here with the nucleus, and then it ejects a bunch of charged particles, and you can see some shower-like things. So now we can go into the event and actually reconstruct the individual tracks and perform particle identification based on the charge that's deposited. So when you do that to this event, what you end up being able to identify is you have a highly ionizing track that stops in the detector, and you can identify that that's a proton, and you know exactly where that proton came from. You have a low ionizing track that overlaps with a second track, so you go down to your other plane, and you can actually see the separation in the 2 charges. So you can see that you had a muon and a pion produced in the initial interaction. And what's more interesting is you can also go through and identify these shower-like events as being photon shower-like events. They all tend to point back to the same interaction vertex. So now I know I have a CCQE, a charge current quasi-elastic event, that also gave me 2 pi zeros that then decayed to photons in the forward boosted direction. So I can really dig into all of the nitty-gritty details of what's happening in each neutrino interaction. What's really great is you no longer have to classify events as being charged current quasi-elastic, neutral current pi 0. You can say I have a 1 muon, 1 proton, and 2 pi 0 event, and I can actually count and classify that event specifically. So it allows me to understand both the nuclear physics that's going on as well as the implications for particle physics. So it really makes it a powerful detector technology.
So the color coding that you had in the previous slide,
Yep.
Was that the charge basically?
That's the charge, yeah. So the more red, the more charge. And this is the collection plane, that's why you see it's more vibrant. And this is the induction plane. So this was only a 2-plane detector in this particular example. So, I've told you about how everything happens inside of the time projection chamber. I should tell you a little bit about the vessels we use to hold the argon, right? The argon has to be kept at 87 degrees Kelvin in order to stay in the liquid phase. So you can't just put it in any old pot. You need some sort of insulated vessel. So there's a couple of different strategies that are used here. Initially, for small detectors, we used a vacuum-jacketed cryostat, meaning that we had an outer cryostat, we vacuum evacuated that area, and then we had an inner cryostat that actually held the liquid argon and the detector itself. Well, that's fine when you have something small and you can pump that down, but as you go to larger experiments, you can't pull a vacuum on something that large easily. So then, for example, in the MicroBooNE cryostat, we have a large circular cryostat that we're kind of literally just going to spray with 6 inches of foam. We're going to do what you do to your house and just insulate the entire outside in order to maintain it. And this is also fine for something about this size. Now, if you want to go really big, much, much bigger than MicroBooNE, you've got to go and borrow something that already exists out in industry. So there's this technology called a membrane cryostat. And a membrane cryostat is really much less sophisticated than it sounds. It's steel with wood and polyurethane foam and all of this pushed together. And then this is actually what provides your volume that your argon lives in. And just for scale, that's a person, and this is what they use for liquid gas tankers to transport it around. So this is already a well-known and understood technology that you can scale up to really big sizes. And as an example, there's a 35-ton membrane cryostat that was constructed at Fermilab that actually just this last month demonstrated they were able to get pure argon circulating in it for the first time at 35 tons. So this was a really exciting result that was highlighted in Fermilab today, like 2 days ago. So this is a really important thing that just happened, showing that we know how to build these things ourselves. So I've told you that we need the electric field a little bit. I'm going to tell you a little more about the details of how our detector works. So the basic idea is if you have a high potential here, or in this case, minus 128 kilovolts, so it's a low potential, and then you have ground here, this is what sets up your electric field. So you have a cathode plane on one side. In the case of MicroBooNE, it's a bunch of stainless steel plates. In ArgoNeuT, this was G10 with copper shielding plated onto it. And so the goal is to get the maximum amount of charge, so you need a really uniform electric field. So what you do is you step down that field incrementally by going from tube to tube to tube. You put a resistor chain between it, so you bring the potential from minus 128 kilovolts to 0 in small little increments, and this sets up very uniform electric field the whole way down. So you're able to uniformly drift that charge over from your interaction to where your collection wires, and your collection wires would live somewhere over here, or in the case of ArgoNeuT, they'd live over here. So there's a whole lot more that goes into liquid argon TPCs that I really don't have time to tell you about, but I'd love to tell you more as the time comes. There's all kinds of interesting physics that goes into achieving the purity that's necessary in order to do this, as well as how do you cool down your liquid nitrogen and your liquid argon, keep it cool, circulate it. All the studies that go into electron mobility and recombination. There was just a 2-day conference on high voltage with liquid nobles in general at Fermilab. And the light detection system, there was a 3-day conference about that. So you'll just have to invite me back someday to tell you about all this cool physics as well. And I'm going to move on and tell you about the experiments specifically that utilize this technology. So the first experiment I want to tell you about is the Argon neutrino test stand, or we abbreviate that ArgoNeuT. So ArgoNeuT was actually the first liquid argon TPC in a neutrino beam in the US ever. This technology had been demonstrated in other places, but this was the first time we were going to put it in a place where there was a lot of interactions to actually see what it could do. So what you're looking at here is you're looking at it straight on. This is where the sense wires are. Unfortunately, these tensioning brackets were kind of bolted on last second, so they look super ugly. And then the readout electronics. And this is the TPC. The TPC's drift direction is from the cathode to the anode, and this was placed in our vacuum-jacketed cryostat. And here you can actually see ArgoNeuT with its bathtub in operation. So ArgoNeuT was located in the neutrinos from the main injector, or the NUMI beam at Fermilab, and it was actually down there right in front of the Minos near detector. This was really a great opportunity because we could use the Minos near detector. Remember I told you this was steel scintillator panels all the way along. It was actually magnetized as well. So what we could do is we could utilize Minos as a muon spectrometer in some sense. So you get a muon interaction in neutrino in ArgoNeuT, you extrapolate where that muon should go, and you look for a track in Minos. This gave you momentum determination and sign determination for free in a lot of ways, and there's many, many thanks to the Minos collaboration for building such a nice detector that we could use. So, of course, I don't expect you to know all the details of what ArgoNeuT was, but I'll give you the Cliff Notes version of how the TPC worked. It was a really small TPC. It was only 0.26 tons of active mass. It was about half a meter tall, half a meter wide, and about 1 meter long. So a really small, sit on your desk sort of TPC. It only had 480 wires, those are our readout channels, at 4 millimeter pitch. That's the distance between each of the wires was 4 millimeters, and the distance from plane to plane was 4 millimeters. And this one didn't have a light detection system. It was a purely R&D situation to get in terms of operation. So ArgoNeuT took data from late 2009 to early 2010. It had 2 weeks in neutrino mode and 4 weeks in anti-neutrino mode, and it collected an absolute variety of high-quality neutrino data, somewhere between 0.1 GeV and 20 GeV, because the NUMI beam has a really broad energy base. So in addition to being an R&D detector, we could actually do real physics with this detector. Specifically, measure for the first time neutrino-argon cross-sections that turn out to be very important. We could study how to calibrate these detectors. We could look into some of these nuclear effects that really matter for neutrino interactions that were previously not able to be detected, but because of this resolution power we have with this technology, we can really study these, as well as develop automated reconstruction techniques, which are important for the next generation Argon neutrino detectors. So there are a few papers that are out that have gone through this laborious process outlined in this cartoon, and there are a few papers in the pipeline that are somewhere next to the hatchet person that will be coming out soon.
So can I ask you, how do you trigger them if you don't have any light collection in them?
So in this one, we receive a trigger that the beam is coming from the beam spill, and we just read out continuously, and it was small enough that we could just buffer the whole data stream. So the first sample of data the first paper that came out of ArgoNeuT came out in 2012, and this was actually just a really simple analysis looking for muons that went through the detector. Nothing terribly sophisticated, but what it did is it showed that we could do both angular reconstruction and calorimetry to identify these muons. So you had muons that were created in the rock and somewhere nearby, and you just looked for through-going muons that were then matched to Minos. And what's really interesting is you can see that the energy as a function of distance profile exactly matches a minimum ionizing track. That's what you expect for muons. And you can measure the angular resolution, and you'll notice that this isn't centered at 0. It's slightly tilted down, but it should be because the NUMI beam is pointed down so that the neutrinos go from Fermilab to Minnesota. So you would expect them to have this 3 degrees down tilt, which is exactly what we measured. So this is a really exciting result just in terms of showing that the detector is working, but now you want to go further and you want to do some physics with this. So the next paper came out was what we call the inclusive muon neutrino charge current differential cross-section. For people who don't speak neutrino physics, basically what we did is we just took the last the last paper and built on it. We said, let's look for muons that were created from a neutrino interaction in the detector. Let's make sure that those muons are reconstructed and matched to Minos. So now we can tell that we have a muon, and we know the muon's momentum and its sign, and we charge sign select for mu minuses, meaning we're only looking for interactions that came from a regular muon neutrino, not an anti-neutrino. And so you can see that we were able to measure the cross-section, the differential cross-section, and we have our point now in the PDG, the first neutrino-argon cross-section ever measured. And this was only with the very first 2 weeks of data that we got out of this detector. Now I told you a little bit about how charge recombination works and some of the physics that goes into it. We actually were able to measure this in the ArgoNeuT detector by looking at what we call highly ionizing particles, basically protons. If you had a proton that was created and stopped in your detector, you could identify the proton using its, how the energy went as a function of distance. And then you would measure how much charge versus what you would expect versus what you would find. The distance of the proton track tells you how energetic the proton was. Then you measure how much charge you have, and you can do this as a function of angle to tell you, is it going away, is it further to, what was the electric field at the time. And what's really interesting is that our results were consistent with other people, the Icarus experiment that had done, showing that we understood the DEDX profile, we could identify our protons. And then we also were able to measure this as a function of angle, and the important result that came out of this is that the angular dependence of how the muon, or how the protons were pointed versus the charge recombination turned out to be a really low effect, like 5 or 10%. But the leading theory, this Jaffe-Calorimeter theory, expected a 25% loss in the charge recombination. So what this tells us is there's something about the way that the charge interacts and drifts over the volume that's not well understood in theory, but that is consistent with what everybody else is seeing. So there's more to learn about this really seemingly simple process of how the charge is collected. So we have a number of papers that are in progress, some of them that I'm working on very directly. So we have an extension to that cross-section that I showed you previously that we did in muon neutrino mode. This is in the anti-neutrino mode, so it's the inclusive anti-neutrino charge current differential cross-section. This is almost the exact same analysis that was done further, except that we have 8 times the data. We're doing this in the anti-neutrino mode, of which we had 4 months worth. Again, we look for an interaction vertex, a track match to Minos, and then we use Minos to sign select, but this time we accept both. We accept mu plus and mu minus, meaning that we're able to measure both cross-sections simultaneously. And we're in the process of getting our flux normalized right now, and this paper should come out hopefully in the next couple months. But again, in the preliminary data, everything looks like it agrees pretty well with the simulation. So it gives us good confidence that we understand how this cross-section is going. One analysis I'm working on, because it becomes much important for later experiments, is this neutral current pi0 analysis. I've already shown you the power that we have for doing this pi0 determination, but now we want to see, can we measure the cross-section itself to see if we understand the rate at which these pi0s are produced. So ArgoNeuT is a really good detector for doing short tracks, and now we want to extend this to electromagnetic showers, which makes it a little more difficult. And this is a particularly insidious background for the new E appearance search I'll tell you about in a little bit. And it's also, turns out to be, I can't pick a topic that's not hard to reconstruct, a notoriously difficult topic to reconstruct. So what I've done is I've utilized the power of its tracking to work backwards and see if we can actually do this going through more simple steps. So the basic idea that we've come up with is we take these electromagnetic showers and break them into track-like segments, meaning when we only look at the real base of the shower, and then we make sure that we can identify that it's a photon shower versus some other minimum ionizing particle. And we do this through a very simple DEDX separation, where if you have a photon that converts to an E plus E minus pair, that's going to be very heavily ionizing. And if you have a minimum ionizing track like a muon or an electron, you're going to have a very low DEDX. And so you can discriminate this just based on the first 2 centimeters of the shower, it turns out, which is great because it gives us a handle on being able to actually reconstruct this event. So we kind of do the inverse of what was done. We're looking for neutral current, meaning we don't want a muon in the event. So we make sure that there is no track match to the Minos detector. We require that we have at least 2 of these clusters in the event. And we require that there's a vertex reconstructed in the detector. That way we know we had an interaction. So just some preliminary studies that we've done on very simple Monte Carlo show that we actually have very good separation between your basic charged particles, and especially your highly ionizing charged particles, and photons coming from pi0. So this shows really good promise in the early stages of Monte Carlo to use this as a discrimination. And now we look at these candidate photon events, and we say, okay, are these candidate photons events consistent with being from a pi0, 2 photons from a pi0? So when we look at the data, you can see that for all reconstructed track segments versus just the reconstructed track segments that we're calling photon candidates, we have the DEDX profile that we're expecting, and we're in the process now of actually turning all of this into a cross-section measurement, and we expect that this come out with both neutrino and anti-neutrino data very shortly. So we're really got a handle, and we think we have a way to start to reconstruct these events, which will become very important for later experiments. Now there are more other analyses that I have the time to tell you with ArgoNeuT, so I want to move on, but I just put them up here. There are really great ones looking for nuclear final state interactions. This is actually going out to PRL very shortly, as well as looking for other backgrounds, these nuclear de-excitation photons and coherent pion production, and all of the suite of normal neutrino physics you'd expect we're able to squeeze out of this incredibly small and R&D-like detector, which shows real promise for this detector technology. So, yeah?
Do you have enough resolution to, when you look at the diphoton system, to see the mass of the pi zero?
So the resolution isn't the problem, containment is our problem. This ArgoNeuT detector is so small that if you get pi zeros much above a GeV or 1.5 GeV, your showers aren't fully contained. And so then you have to make some inference about the pi zero mass, which is really hard. I'm focusing on trying to reconstruct the low energy photons to start with, because otherwise how's anybody going to believe me I have a pi zero? But the full shower containment, we need a larger detector.
But if you have the low energy pi zero and you get the full photons, what's your pi zero mass resolution?
So we haven't made that measurement yet. We're in the process of. The one that was done similar from the Icarus experiment is a few MeV that you expect.
So it's in the few percent level.
Exactly.
Okay.
So I want to tell you about the next generation, kind of the big brother to ArgoNeuT, is the next neutrino detector we're building. This is the MicroBooNE detector. And MicroBooNE actually is finishing construction right now, and we expect to have data in 2014. So let me explain what you're seeing on the slide. This is Daniel Boone standing on a microscope. MicroBooNE? Anybody? No? Okay. So this is when we were installing the detector into the cryostat. We actually just deployed this in December. What I really like about this picture is this grad student who's standing here that I work. This is me up on the ladder, looking at this thing perilously going in. And the system we had for pushing this thing in fell off. And so he's literally holding the whole detector, keeping it from rolling in unexpectedly. Don't worry, it deployed just fine, but this was just a funny snafu that happened. And of course, Ryder Han was there snapping pictures the whole time. And this is what the inside of the TPC looks like from a fisheye view, so it's kind of distorted. So let me give you again the snapshot of what the detector is. It's a TPC that's about 10 meters long, 2.5 meters tall, 2.5 meters wide. The 2.5 meters wide is the drift distance. This will actually be the longest drift distance ever achieved when we do it, for a Argon neutrino detector. We have about 80 tons of active mass. The problem is it's a 170-ton cryostat, but it's a square peg in a round hole. So we lose a lot of that argon volume. We have 8,256 wire channels, which I will know that number in my sleep because I literally installed every single one of them, for better or for worse, by hand, so hopefully they all work. We have 3,456 collection channels, 4,800 induction channels. We have 32, they're 8-inch cryogenic PFTs. I think I told you 12-inch, that was my mistake before, which provide the event T0. And so you can see the PMTs arrayed along here. I think I got the 12-inch because that's the width of our TPV plates. That's what happened with my mistake. You'll notice that they're in this kind of funny configuration. It's because the PMTs had to fit in around these hexagonal bars. So they're not in the most optimal deployment, but they're there to give us just fine T0 reconstruction.
You only put them on one side?
Yes.
It doesn't matter.
Yeah, so because the inside of the detector, you're going to get a lot of reflection from the cathode plane, and you'll expect to be fairly transparent to the photons. You should see plenty of scintillation light. So MicroBooNE will be deployed in the new building called the Fermilab Liquid Argon Test Facility, or LARTF. What's really great about this location is we'll see neutrinos primarily from the booster neutrino beam. This is the same as MiniBooNE saw. But we'll also see an off-axis component from the NUMI beam, which is really great, which means we can kind of run and take neutrino data regardless of what the run plan for Fermilab is. And these two beams provide both low energy and a high energy source of neutrinos, which is complementary depending on what type of physics you want to do next. The booster beam is created from protons on a beryllium target, so you get a mean neutrino energy of about a GeV. Whereas the NUMI beam comes from 120 GeV protons on a carbon target, and that gives you 2 to 20. So you really have two energy regimes you can probe simultaneously with this detector. So why would we build MicroBooNE? Aside from just scaling up detector technology, which is really interesting, onto itself, there's also good physics motivation. So a while ago, this detector that was at Los Alamos called the Liquid Scintillator Neutrino Detector, or LSND, was looking for, from a muon neutrino source, the appearance of electron neutrinos to see the oscillation. And what they observed was way more events of the appearance of electron neutrino than they expected from background. And this is a 3.8 some sigma effect. However, this is a really much disputed result. And people have argued over this over a lot of years. And it could be evidence for new physics. So one way you could get more electron neutrinos showing up is if there was some fourth generation neutrino that occasionally oscillated to your electron neutrino. And this would give you a candidate for it. And the experiment is really defined by the distance from the source and the energy of those neutrinos. So the easiest way to cross-check this is to do another experiment that's at roughly the same L over E, that ratio. So they did, and they called this experiment MicroBooNE, and of course Mother Nature despises experimentalists, so she gave us a different result. So she didn't really tell us anything about the LSND area, the energy range where they saw their anomaly, but instead MicroBooNE sees an excess of electron neutrinos in the low energy bit. So it's something else that's strange. And this effect dominates somewhere between 200 and 500 MeV. So now you've got these two effects and both tell you something really different and kind of strange. And you'll notice from these background plots that this area is dominated from mis-ID'd pi zeros. This is where pi zeros come back into the game, being the dominant background. So MicroBooNE was a liquid scintillator detector. And so the way that they did their identification is they said, look, most electrons and photons look like these fuzzy rings. Muons are nice crisp rings. Protons are, you don't hardly ever see them. And a pi zero with two photons, you should see two crisp rings. But of course, if those pi zeros are highly boosted, you're going to have a hard time mis-IDing one from two. And so you're going to get a tough time to tell the difference. But this is exactly what liquid argon detectors are great at, is this electron-photon separation. So in MicroBooNE, these are of course simulated events we haven't filled with liquid argon yet. What an electron neutrino event looks like and what a pi zero looks like is very, very different. And you can actually go in and utilize that DE, DX information in the very beginning to do that discrimination. So this will give us a really good handle on this oscillation search and hopefully give a decisive, when we have our full 3 years of running, answer to maybe both the MicroBooNE and LSND anomaly, which is really the goal. But we can do more than just oscillation physics with MicroBooNE, which makes it a really interesting detector. And there's a whole suite of things that I don't have time to highlight, unfortunately, in this one seminar. We can do cross-section physics to understand low-energy cross-sections. This will go into longer baseline oscillation searches. And having a really good understanding of these cross-sections is a must for the next generation detectors if you're going to measure things like the mass hierarchy and CP violation. There's a lot of R&D that's also going on with this. I get to be the chair on the R&D physics working group, so I get to hear a lot of the really crazy cool ideas that come across. Two of them that I'll point out is that while MicroBooNE is on the surface and we can't control when a supernova goes off, we can search for low energy electrons, which would be a signature of a supernova giving you electron-like neutrinos, and say to what level can we reconstruct the lowest energy supernova-like events. And this is an example of a 3 MeV electron that still gives you a 3 centimeter by 3 centimeter track. So you get plenty of information out, even in the low energy regime. You can also do a study for proton decay backgrounds. So the golden signature for proton decay that liquid argon competes with your water Cherenkov is this proton goes to K plus and a muon neutrino. This signature is, you're very blind at this in experiments like the Super Kamiokande experiment, but liquid argon detectors have this really clear signature of a kaon decaying to a muon doing an electron. So MicroBooNE can actually look for this signature and start to lay the groundwork for how you would do proton decay searches with these detectors. So I'll quickly tell you about some of the fun things we've got to do in terms of building this detector. Roughly in 2012, we got a pile of parts that showed up and a set of instructions that looked like IKEA instructions, and we were told, make this box. And so, you have to go through there and you've got to clean all these parts because they show up from a machine shop and they're filthy and you need pure argon. So we slowly built up and constructed the whole TPC, and this came together kind of in late 2012, the actual mechanical structure, with of course all the Fermilab technicians doing most of the heavy lifting and us being there just to kind of help and supervise. They don't need supervision. And then in early 2013, we finished major construction of the TPC. It looks like it was going to look like. And to much less fanfare than when the G-2 ring showed up, our Cryostat showed up at Fermilab, which was every bit as big as that G-2 ring, but just nobody cared about it as much. And so we got to test fit to make sure the square peg fit in the round hole, and sure enough it did, which was good. That gave us good assurance that we had built the thing to the right dimensions and hadn't left any parts off. And we actually did it with some of our systems installed. We had some PMTs, these are just test PMTs, and some fake wires installed as well, just to make sure there were no interferences. And then the wires themselves, this is something that I got to take a lot of part in. These are 8,256, 150 micron stainless steel wires. So they're roughly like the smallest string on a guitar, is a good thing to think about. So they're pretty robust wires. And these are individually wound on a machine around these brass ferrules, and then human hands, one by one, place them on the electronics board. Then we test the electronics board, then we close the electronics board up. And then I got to lead a team of 13 or so postdocs and grad students to actually install all of the wires on the TPC itself once we finished construction. And sure enough, you can see in this picture from the different reflections, all 3 planes of wires were installed successfully and tested. We were able to install the cold motherboards as well. That went swimmingly well, and cable everything up. So this exercise allowed us to have both test our data acquisition system and make sure all the TPC wires were working, and it all checked out just beautifully. Right before, we went ahead and installed it, and so I showed you one picture before as we were installing it, just to show you what I was staring at, these really small clearances which had me like biting my nails the whole time. And this just happened in December of 2013. Your first persons to see this outside of if you've been to Fermilab or stare at our webcam, which they made us set up, is the TPC is now in, and next week we'll actually weld the end cap on and get ready to move it over to LARTF. So the experiment is going to happen, and it's going to start up in the next few months. So it's really exciting times. So what comes next? I've told you about all these really great things we're doing with liquid argon TPCs. Where are we going with all of this stuff? Well, of course, with MicroBooNE, now we're moving into the commissioning and installation phase. We have this nice new pristine building. We have dewars filled with liquid nitrogen and liquid argon just waiting for us. We have our experimental pit where the MicroBooNE cryostat gets picked up by a crane, dropped through the hole, not dropped, placed nicely through the hole, and put on these giant foam saddles. It then gets insulated up, cabled up, all of the piping goes on, and we expect, and then we'll start commissioning with cosmic ray data as soon as we have liquid in the detector. And then we'll make, as soon as we can show that we can reconstruct tracks, we'll put in the request to Fermilab run plan and say we're ready for neutrinos, and the data taking error will be here. So we expect to have our first neutrinos from the booster beam later this year, and if NUMI's already running, we'll already have neutrino interactions from NUMI, which will be great. So we're doing all of this really hard work with MicroBooNE, but this isn't the only efforts that are going into the liquid argon TPC capabilities. There's another experiment I haven't even had time to tell you about, which is called liquid argon in a test beam, or abbreviated to LARIAT. So if you have a new detector and you have a new technology, the first thing you do is calibrate it. You put it somewhere where you understand the incident energy and you see if that's what you get out. But this hasn't been done. So this is a quote somebody said to me at Fermilab, is every new detector, calorimeters, trackers, etc., is calibrated before physics application. We did it the other way around. We used this thing for physics, and we're like, oh yeah, we should calibrate this to a more higher degree of precision. So an important point that came out of a 2009 review was said, we should know these really well, and one of the ways we should do this is let's put a TPC in the test beam. This is great about Fermilab, is we have these test beams that can tell us we are putting this type of particle in with this known momentum, and you can really start to calibrate the detector. So we utilize what we already have on hand. ArgoNeuT was sitting around, it wasn't taking data anymore. We repurposed the cryostat. We outfitted the TPC so that it could have PMT, so we could do light detection as well. And we lined the inside with wavelength shifting foil. And now we're going to put it in the MTest center. This is the test beam facility in Fermilab. So what this is a beam of protons comes in. You can siphon off a secondary beam that gives you about 300,000 particles per spill. And then from that, it got cut off, we make a tertiary beam so that we can select off pions, muons, protons, electrons, and fire them in at a very well-known energy. And this will give us really detailed responses for different momentum, so we'll be able to calibrate the detector. And we'll be able to do a lot of other physics, which is even more interesting. We can do charge sign determination without the presence of a magnetic field, maybe. This is what we're looking into. Because we know that if you have a mu plus, this would come from an antineutrino, for example, this only decays with the emission of an E plus at a very well-known energy spectrum. Whereas if you have a mu minus, the mu minus will capture on a nuclei, and 75% of the time it'll give you a photon, the other times it'll decay. So now the question is, if I fire in known mu plus and mu minuses, can I look for these distinct signatures to tell me sign determination without a magnetic field? So it gives you a way of not having to magnetize a large volume of liquid argon. Then as well, you can also do really well measured electron-photon separation studies by firing in electrons of known energy, have something that will cause them to Bremsstrahl along, and so then you'll have electrons and photons in the same event, and you'll know their energy based on the material you put in front. So this gives us a chance to really dig into calibrating these detectors to a high degree. So construction and commissioning are getting ready to commence, and we expect operations in the summer of 2014. So this is going to come online at kind of a prime time for MicroBooNE, when we're going to just start getting data, and we'll have this source of calibrations as well. Of course, we don't stop there. If you have one good idea, then more good ideas is even better. So there's a talk that was given actually at the Fermilab PAC just today about this staged multi-liquid argon TPC short baseline neutrino programs. We need to come up with better names for these things. But the idea is you already have an infrastructure, you already have a neutrino beam. Why not fully invest and find a way that you can build a short baseline program at Fermilab? So the proposal is really a three-phase proposal. The first phase is happening. This is MicroBooNE, deployed where it is, here about 470 meters from where the booster beam comes. The second phase is to actually build a near detector relative to MicroBooNE. This would be a 82-ton active volume TPC, about 100 meters from the source of the beam. And then if this goes successfully, the long-term plans is to build a very large 1 kiloton detector, 700 meters from the source of the beam. So you'd get a 3-detector configuration. I'm going to focus on just the near detector for the moment, because what's great about this is we can utilize a lot of the information that we already want. We can deploy in the SciBooNE hall. We don't have to build a new detector hall. You can also start to utilize some of the designs for future detectors and test if they're going to work here and now. So there's these new designs for the TPC. You'll see that this looks much, much different than it did before. This is more like the Icarus setup, where you have a cathode plane in the center, wire planes on either side. And so if you're looking from the top, you've got the neutrino beam coming in, and then you'll have your detector there. This is what it looks like from the side. So you can utilize and test a whole suite of just detector R&D through deploying a near detector. And as well as you can start to do new physics in this sort of deployment, where you have a near detector and a far detector. So the physics that this scenario gives you that's not given to you with MicroBooNE alone is you have an improved sensitivity to the mini-BOON low energy excess, because you have 2 detectors measuring it. You can actually look for disappearance of muon neutrinos to see if you see so many in this detector, do you see the same number here? You can't do that without a near detector. As well as neutral current disappearance and dark matter searches. So if you run in a beam off configuration where you crash the BNB into off target, there's a possibility that you can produce axions, and then would you see those in the near detector? That's the basic idea. And this was just presented at the PAC, so there are slides to go look at. And of course, the real long vision for this is to build a many kiloton version of the liquid argon TPC in the experiment called the long baseline neutrino experiment. It's 34 kilotons deep underground is the idea, and optimized for a distance and oscillation to let you get at some of the fundamental physics that we haven't yet to measure. And so what you need is a powerful neutrino beam and a big detector. And I will just flash this slide since I'm out of time. But basically the idea is that as a function of energy, your energy spectrum will look different in this detector configuration, whether or not CP, what the CP angle is, whether or not you're in the inverted or normal hierarchy, as well as you can do this in the different neutrino chains. So it opens up new physics and allows you to capitalize on all the R&D that you've been doing. So conclusion. I hope I conveyed my excitement for this detector technology. I think it's a really interesting phase it's moving into in neutrino physics. ArgoNeuT will continue to squeeze as much information out until there's literally no more papers to be pushed out of this detector. And MicroBooNE expects to start taking data in 2014. And I think there really is a bright and growing future in LAR TPC technology, with many experiments continuing to push the envelope. So thank you very much for your attention.
Other questions for Jonathan?
How long are the signals, and what is the frequency of events?
So the frequency of events is sub 100 hertz. It depends on where you are, right? The near detector proposal will have a much higher. And then the signal itself is a 1.6 microsecond drift. So you're reading out that wire.
That's a drift time, but how?
So you're reading out the wires that whole time, right? And then your pulse shape itself is some, very small fraction of that. So we count it in terms of the time ticks. We bin it such that 1.6 microseconds is 3,200 time ticks. The rise and fall of a typical pulse is on the order of 20 time ticks. That's just to set the scale.
Is charge build up in any way?
So that's an interesting point. So one of the things you have to be worried about with surface operation is you have cosmic ray muons bombarding your detector. And if your argon flow rate is such that you're not also dissipating the residual charge that's building up, you could get space charge to build up. Now MicroBooNE has a system to try to calibrate this out. It's a UV laser where they shoot a UV laser track that should be perfectly straight, look for distortions in that track as it's collected for the wires, and that will tell you if you have charge buildup. Now, we haven't operated these detectors on the surface, so we don't know of this scale. The smaller ones have operated. So we don't know if space charge is going to be a huge concern, but that's one of the things we have to discover with MicroBooNE.
You had some thoughts on page 51 and 54, where you were comparing some of your data with some simulations. Yeah, so it was this one and 51. A lot of them, there seems to be a recurring theme that you get the tails really nice, but your peaks always seem to be kind of...
That's right. Yes, you're absolutely right. So a lot of this comes down to by changing what you model for your nuclear models in your Monte Carlo, that peak and what it looks like changes. So when we compare these sort of results, this is Genie Monte Carlo. If we compare this to GBoo or some of the other Monte Carlo simulators that use different assumptions about your initial and final states that are going to come in and out of the nucleus, that peak shifts. So it's telling us physics, exactly. It's telling us that there is some misunderstood physics in terms of the neutrino interaction. It's not just our Monte Carlo isn't tuned right. There's some disagreement on what's really happening there. So that's one of the questions that we're trying to push out to the theorists community that work on these models and say, what's going on and why, essentially.
So these are the muons that are just coming out, not the neutrino as it interacts out.
That's right. You infer backwards what the neutrino energy is.
Right.
Yeah. Yeah.
Would you say a few words about Theta-13 and LBNE?
Yes, what would you like? So Theta-13 was measured just recently, and it was measured large, which gives us an indication that LB&E will be more sensitive than previously thought to delta CP, to the CP violating phase, as well as possibly even getting the mass hierarchy. Because since Theta-13 is large, your oscillation probability is large for having the oscillation occur in that mode. So in that way, it's good for LB&E. It makes a compelling case. Now, if LB&E still had on its bullet list measure Theta-13, we're out of that game. That's been measured and been measured incredibly well by others. So I think you look at that opportunity that came and you say, great, because now we're going to have we'll need less statistics to be as sensitive to the oscillation physics that we're looking for. Yeah.
The charge current event, and so how challenge of the leptons to reconstruct almost 100% of it or something else?
So if the lepton is stopping in the detector, it's nearly 100% because you're able to get all of it. But most of these are exiting, right? They're matched to Minos in this particular example. So the matched ones, you then have to go backwards and say, well, what was the momentum that was lost through this distance and how did it range out essentially? So there you're less, and you're probably, if you're really worried about the energy, you're probably at the 80% level. But if you have full containment, we believe we're near 100% energy reconstruction. And this is one of the things with having MicroBooNE, a larger detector, we'll get to actually test, right, and see how well we're going to do with reconstructing those muons over large distances. Yeah?
What about tau neutrinos? All you've shown is electron and muon. Is that suppressed by the mass of the tau, so you don't?
So, well, the oscillation from muon to tau is low, right?
Okay.
And so we start with a muon neutrino beam. So your primary oscillation is muon to electron. Then there's also this thing where a lot of the physics is simpler if you just consider the two-flavor case. So neutrino physicists tend to think a lot in just terms of the two-flavor case. There's a full consideration that's done over many of the other oscillation searches. So like what Minos and Nova, what Minos does and what Nova will do, they consider the full three-flavor paradigm and how that fits in. There is an experiment that was running in Gran Sasso, the opera experiment, which everybody knows from the unfortunate measurement of the fastness speed of light, but they were searching for tau neutrino. And over their run, they found, I think, 3 candidate events now, 3 or 4 now. So there's been evidence that you have a muon neutrino oscillating to a tau neutrino. It's just really tough statistics.
No, but muon neutrino can get converted into tau neutrino with a very good probability, but it depends on what's the energy of your beam.
For these energy beams, right? Yeah.
So
yeah,
here
sorry,
you are
you're right.
sensitive to delta M square, which is
Right, yeah, sorry, I left that important part out. You're absolutely right, yeah. Of course, for these energy beams, that's what matters.
Other questions for Jonathan? If not, let's thank our speaker again.